Alright, so now we're going to talk about the second type of improper integrals. These are those that have vertical asymptotes. So the intuitive idea is that these are ones where the height of the graph is infinite. Okay? So, so basically the setup is say f of x is continuous on some region, say, doesn't really matter, except at some point, so some number c, so c would be in this region here, where the function f of x has a vertical asymptote. So remember, vertical asymptote, so that just means that basically as you get closer and closer and closer to c, the graph becomes more and more and more positive, or more and more negative, or differs from different sides. So the picture, you should all remember what vertical asymptotes look like, but you have C, and here's A and B, and everything is groovy, but then maybe you have some big spike that occurs at C. So the graph has a big spike. But aside from that big spike, everything else is good. Okay. So the question is, can we still integrate over regions that have big spikes? And the answer is sometimes we can, but anytime we're trying to do an integral over a spike region, these are also referred to as improper integrals. So this is the second type of improper integral. Okay, and so then we could just define it. In such a situation, we can still integrate over the region from A to B, and we just have to basically split it up by the two spikes. So the spike occurs at C, so the first thing we can do is we can just split it up from the lower bound to the spike, and then continue going on from the spike to the upper bound. But we have to be careful here, because what does this mean? So here and here is where we have the asymptote. So, we can't just plug in. If we could, like by the fundamental theory of calculus, if you were to plug in, well, you're calculating antiderivative, but still you're like plugging into some function that could be infinite. In fact, that is infinite. So, to actually define how we do these, again, we just use limits. So this first integral would be taking the limit as some parameter, let's say s, it's just some number. It's going to approach the asymptote. This means from the left, and we're just going to do the integral from a to that parameter of f of dx. And then for this, we also have to take the limit of some other parameter as it approaches c from the right. And now we're just going to integrate from that parameter up to b of f of x dx. And so this is formally the definition of how we calculate these integrals. So here is the definition. So this is the definition of integral from a to b with an asymptote at the point c. So even though there's an asymptote, we can still actually talk about calculating the integral. So again, intuitively what's going on is just like this picture over here. You now have some vertical asymptote, so you're considering a graph, has some vertical asymptote over here, and so maybe the graph looks something like that. And it keeps getting larger and larger and larger it's getting higher and higher and higher, the picture is just an approximation, and so like the idea is, well, what would this area be? You know, again, think about it intuitively, it doesn't quite make sense because, you know, it's getting higher and higher and higher and higher, so there's this infinite height. But in some cases, you can still actually calculate this integral using these limits, and you actually get a finite number. And these types of integrals are also referred to as improper integrals. So improper integrals are sort of like definite integrals where the regions are infinite, and that can occur in two different ways. Either the type 1 is the base is infinite, so the limits of integration are infinite. In case 2, which is what we're talking about now, is if there's an asymptote, so that means if the height is actually infinite. So now let's just do some examples. So the first example will be the integral from 0 to 1 of 1 over the square root of x dx. And so you may not be comfortable with the graph of this function, but we know that we can never divide by 0, and the square root of 0 is still 0. So if we're trying to calculate this integral, then for those values of x that are getting closer and closer and closer to 0, so if you approach 0, so here 0 is the lower bound, so you're integrating from 0 to 1, so that means you're considering when you have values that are really, really close to 0, we see that the graph, the output defined by this 1 over square root of x is going to be really, 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 really big. So you can sort of just imagine that the graph is going to have this vertical asymptote, because dividing by the square root of a really, really small thing, that's still like dividing by something really, really, really tiny. When you divide by something tiny, you get something very big. Anyways, and so, but that's okay. We'll just work through this carefully. So the point is, we can't just plug in 0 anywhere, but it's really not that big a deal in this case. So formally, you just take, let's take the limit as some parameter, say s approaches 0 from the positive direction of the integral from s to 1 of 1 over square root of x dx. So to do this, we'll use the power rule. So let's first rewrite this. That's x to the negative 1/2 power dx. We're integrating that from s to 1. That's an s. And now inside of the limit, we will use the power rule. And the fundamental theorem of calculus, the power rule says you increase the power by 1, negative 1/2 plus 1 becomes positive 1/2, and you divide by the resulting power. That's the power rule for integrating, and then by the fundamental theorem of calculus, we have to evaluate that at the two endpoints. First evaluate at the 1, and subtract from it, evaluating it at s. So I'll just write that out so you can see it before we take the limit. So that's, 1 to the 1/2 power divided by 1/2 minus s to the 1/2 power divided by 1/2. Okay, and we can all divide by fractions, so, well, you should be able to finish this on your own, but so that's the limit. Dividing by 1/2 is the same as multiplying by 2 over 1, so that becomes 2 times 1 to the 1/2 power minus 2 times s to the 1/2 power. We're taking the limit over s here, but as s goes to 0, s to the 1/2 also goes to 0, so that when we actually take the limit, this will just go away as s goes to 0. So this limit is actually just 2. Yay! So again, if you sort of go back to the sketchy picture, we're like calculating the area of this region here, okay? And the height keeps getting bigger and bigger and bigger and bigger and bigger. It goes on forever. It has a vertical asymptote, and so it's kind of quirky that when we evaluate this definite integral, we actually get a finite number, in this case the number 2.